Let us consider a system with m equations and m variables. For example, something like 2x1 plus 3x2 minus x3 plus x4 equal 2, 4x1 minus 2x2 plus 4x4 equals 6, 3x1 plus x2 minus x3 plus x4 equals 7. Then in this case, n is equal 4 and m is equal 3. We know that if we do some operations with these equations, we get an equivalent system in the sense that the two systems has the same solution. For example, we can swap two of the equations and we get an equivalent system. And what I want to point out is that it doesn't matter if whatever you do goes toward a better system or not, the two equations are going to be equivalent. For example, here I can change equation 1. I can change it with equation 1 minus 3 times equation 3. When I do this change, I will get equation 1 is the one that is changing. Then I keep the other ones exactly the same. And I'm going to do this. I'm going to do 2x1 plus 3x2 minus x3 plus x4 equal 2. And I'm going to do minus 3 times this. It will be 3 times this. It will be 12x1 minus 6x2 plus 12x4 equal 18. Then I will get, I'm doing this minus this, I will get negative 10 x1 plus 9 x2 minus x3 minus 11 x4 equal negative 16. Then this is the new equation 1. Negative 10 x1 plus 9 x2 minus x3 minus 11 x4 equal negative 16. These two equations are equivalent, and it doesn't matter if this equation looks worse than the first one, but they are equivalent in the sense that the solution of this system of equations is equivalent to the solution of this system of equations. We're going to be learning what type of equation is better. For example, here this change is difficult to tell that this system of equation looks better than this system of equation. Then we're going to later on explain what we mean by having a better system of equations. But by now, I'm going to somehow save some ink and keep the same information. In the sense that instead of writing the variables, we're going to write matrices. For example, here, the information that we have in this system is the same information that we have in this system here. A11, the information that we have in this matrix. A12, A1n, B1, A21, A22, A2n, B2, AM1, AM2, AMN equal, BM. This is an M times M plus 1 matrix, which, by the way, this matrix is called the matrix of the system. And the important observation is that if we know the matrix of the system, we can't write the system. And if we have the system, then we can write the matrix of the system. Then somehow all the information of this system is here. As an example, for this system, we have this matrix, 2, 3, -1, 1, 2, and here we have 4, -2, 0, 4, 6, 3, 1, -1, 1, and 7. This is the matrix of this system. And the matrix of this system would be -10, 9, -1, -11, -16, 4, -2, 4, so here is 0, 4, 6, 3, 1, -1, 1, and 7. Then, instead of doing these operations with the variables, we can do these operations with the matrices, right? And in general, we're going to say that these two matrices, let's say A, the matrix A, and the matrix B, we're going to say that the matrix A and B are row equivalent. Please do this homework. Keep in mind that the operations that we're allowed to do are swapping two equations, multiplying one equation by a number that is different from 0, and adding to a given equation a multiple of another equation. With that in mind, let's suppose we have a matrix C11, C12, C1K, CL1, CL2, CLK, and then there are some rows here. And then we're going to define the operation of swapping two rows. Swapping two, multiplying one row by a non-zero number, and 3, changing one row by the row itself plus a multiple of another row. Then these are going to be called row operations, and then we're going to say that two matrices with the same dimension, D11, D12, D1K, DL1, DL2, DLK are going to be equivalent if I can get this matrix out of this after a finite collection of these row operations. As an example, these two are equivalent, are row equivalent because this was obtained by changing row 1 by row 1 minus 3 times row 2. An important observation is that this definition of being row equivalent is independent of the fact if they represent a system. Notice that here, that's the reason I changed the notation to C's and D's, because they don't have to come from a system. You can have, the definition works regardless if this comes from a system or not. And the good thing is that when they come from a system, then the system represented by this matrix has the same solution as the system represented by this matrix. That's good to know that when they are representing systems, the two systems have the same solution, but in general, they don't need to come from a system of equations. Okay, this is it for this video. Please do this homework.